I'm Daniel Levine, and this is the Bio Report. Leukemia once threatened Aaron Viny's life, but now it defines his mission. Diagnosed with acute lymphoblastic leukemia as a college student, he survived chemotherapy, central nervous system relapse, and an allogeneic stem cell transplant from his younger brother, an experience that made him aware of both the power and toxicity of conventional cancer care. Today, as a hematologist-oncologist and laboratory researcher at Columbia University, Viny is helping reimagine how we treat blood cancers by shifting from blunt cell-killing approaches to precision strategies that rewire malignant cells in their ecosystems. We spoke to Viny, assistant professor of medicine at Columbia University Vagelos College of Physicians and Surgeons, about the case for thinking of hematological cancers as regulatory problems rather than focusing on genetic mutations, the potential for looking at epigenetic activators and deactivators of genes to treat them, and how he's harnessing new technology to look at cell surface proteins to distinguish regenerating marrow from refractory leukemia. Aaron, thanks for joining us.
Great to be here.
We're going to talk about hematological cancers, traditional therapeutic approaches to developing therapies that kill cancers, and the case for reframing that approach to these diseases by seeking to rewire or reprogram cancer cells. I'd like to start with your own history. You were diagnosed with acute lymphoblastic leukemia more than 20 years ago. What happened?
Yeah, I guess that's one way to just kind of dive right into it. Sure. So I love the framing of killing cancer cells with essentially poisons and dichotomizing that from trying to reprogram and rewire cancer cells, which has been a lot of the effort of some of our research focus. But personally, yes, indeed, I was diagnosed with acute lymphoblastic leukemia when I was 20 years old. I was a junior in college, and this is a disease that is prevalent rather uniquely both across young children, older adults, and also in people who are kind of termed the adolescent and young adult stage. So I was an AYA patient with a disease that's largely been classified and thought of as a pediatric leukemia, which creates some additional layers of complexity. And so, what leukemia is at its core, and I think this will be relevant for some of our discussions later, is you have these important stem cells in your bone marrow, and all of the stem cells that you're ever going to have, you're born with. Those stem cells mostly remain dormant and quiescent, and only a small population of those stem cells at any given time are the ones that are repopulating your blood. They're making the red blood cells that carry oxygen. They're making the white blood cells that help fight infection. And they're making the platelets that help you clot the blood if you have any tissue injury. And importantly, they also have the ability to self-renew. And so over your lifetime of, say, 80 to 100 years, you have a constant pool, you have a constant source of blood production. And so that characteristic of that stem cell being able to self-renew and make exact copies of itself is the value of what adds this lifelong blood formation capability, but it also is the liability that can lead to cancer because that cell is immortalized. And that immortalization, that stem cell program is exactly what cancer cells use, both in the blood and in solid tumors, to be able to grow without constraint of their environment. So, for example, if you are, if you have an infection, signals go to your bone marrow to make lots more white blood cells to fight the infection. If you're Lance Armstrong and you're trying to cheat in the Tour de France and you inject yourself with a hormone EPO to tell your bone marrow to make more red blood cells, they're going to make more red blood cells. So these cells in the bone marrow, they're not just working on autopilot, they're constantly surveilling the environment and responding in kind. But if there are mutations, either because of a change in the DNA sequence or because one part of a chromosome has broken off and translocated to another part of the chromosome, then that cell, which has this limitless capability to divide, no longer is responding to those signals that it should be receiving. And a cancer cell that can divide and no longer can function, that's what leukemia is. So I was diagnosed with leukemia, and the symptoms of leukemia are exactly, describing what the pathology is. You can't make red blood cells, so you're anemic and you're tired. You can't make white blood cells, so you're at risk for infections, and you can't make platelets, and so you're bruising more easily, and you might be, having bleeding from your gums or bleeding from your nose and that sort of thing. And so that's what happened to me. I was actually on a ski trip with a couple of friends, and I'll say straight out, I'm a better skier than the folks that I was skiing with when my buddies were on winter break. But man, I was tired. I was sucking wind at the bottom of every hill, and clearly something must be wrong. So I did what any other college kid would do, which is I'm feeling really tired all the time and something must be up. I went to the student health services and they took some blood and they said, yeah, you probably got, mononucleosis, Epstein-Barr virus. And they did some testing for that, but they also took a CBC, which showed that I had large immature blood cells in my blood, which is the harbinger of these leukemia cells because they can't mature. They will leak out of the bone marrow into the blood, and then you see these abnormal cells that you have no business seeing in somebody's blood. Um, I was in college at the University of Michigan. My family and I grew up in Cleveland, Ohio. So I called my folks and said, hey, who do we know who's a hematologist? And we made some phone calls and I drove home. And the next day I was seen by Dr. Alan Lichten at the Cleveland Clinic Foundation, who diagnosed me with acute lymphoblastic leukemia. Over the next, 4 months, I got intensive chemotherapy. These are poisons aimed at killing dividing cells. So because these cells are rapidly dividing, you give essentially anti-metabolites and chemicals that break and intercalate DNA, and cells that are rapidly dividing are going to be most sensitive to that. But you got lots of cells that are dividing in your body, your hair follicles, the mucosal lining from your lips all the way through your gastrointestinal tract, your skin, and that explains all the side effects people get from chemo. They get nausea, they get diarrhea, they get rashes, they lose their hair, and their blood counts go down because these are the most rapidly dividing cells that you've got in your body. I went through chemotherapy for about 4 months, and then unfortunately, the leukemia, which originally went away, found a place to hide in my spinal fluid, and so that required some treatment directly into the spinal fluid that kind of washes around your brain and your spinal column. And knowing that was the case, we know that at that point that leukemia is not curable with chemotherapy alone anymore. Today, we've got some really fantastic tools like CAR T cell therapy for patients like that. But at that time, my only option was a allogeneic stem cell transplant, meaning I got a new immune system. This from my little brother, who was 10 years younger. And so they gave me some chemotherapy to ensure my body would accept this new immune system. It took over in my bone marrow. And so now I have his blood type and his blood markers taking residence in my bone marrow. So now my bone marrow stem cells that I was born with have now been replaced with his. And they continue to make blood for me over my lifetime. They also see anything that is not recognized as self, as foreign. And because of that, they identify, attack, and kill any rogue residual leukemia cells that might have been lying dormant, and then also identify and attack any organs in my body that are um, antigenically or immune distinct. So your liver, your skin, your gut, and that's something called graft versus host disease. I had, fortunately, minimal to moderate graft versus host disease, and knock on wood, next week will be 23 years since my diagnosis, and now I get the privilege of taking care of patients who suffer from these malignancies. I get the privilege of running a research laboratory aimed at trying to identify new classes of therapies that are more efficacious, less toxic for these terrible diseases. And I get to kind of take one of the more challenging and unfortunate aspects of things that happened to me over my lifetime and try to give meaning to the crap that I went through by trying to do something for other folks. So I know that was a bit of a long-winded answer to it. Certainly, it's trying to summarize a lifetime of biology, therapy, and psychology into a couple of minutes. So apologies.
How have treatments for hematological cancers evolved since your days as a patient?
Yeah, no, they really have. I've been fortunate to be part of a guidelines council through the American Society of Hematology. So we've just put out the guidelines for how to treat patients with acute lymphoblastic leukemia who are adolescents and young adults, and our consensus recommendations of how best to treat them, because there's so much involved, and it's not just the therapies. The chemotherapy, in large part, despite our major efforts, in many cases has unfortunately not changed. But we do a lot of things better. One is we're much better at treating and monitoring for the infectious complications, and that's been a huge advantage. Two is for not all patients, but for some of the patients, we're identifying precision therapeutics, meaning if we find specific mutations in a person's type of leukemia, are there drugs that are unique and specific towards that? So, for example, my type of leukemia was not driven by a fusion between two chromosomes called the Philadelphia chromosome. But many patients with acute lymphoblastic leukemia are. It used to be a very poor marker that if you had Philadelphia positive ALL, acute lymphoblastic leukemia, your disease was going to be much more challenging, and going directly to a transplant as opposed to trying chemotherapy first was often the recommendation, and the chemotherapy was much more intensive. But now we have small molecule inhibitors, and in these patients, we have now, not for everybody, but for many patients, moved entirely to a chemo-free regimen that has a remission rate that approaches or achieves 100% remission rate for every single patient. That's just an amazing accomplishment to take a disease that was once the poorer risk, and now, because of the advances in medical science and the development, the understanding of the underpinnings of the molecular genetics that drives leukemia, to identify small molecule inhibitors that have absolutely been game changers towards how we treat patients. I mean, this is the Kool-Aid I wake up every morning, drinking myself and serving to my laboratory and my team, because there's no question that the patients who need our help, who we do not have therapies yet for, um, they need it desperately. And we can look back at ALL in kids before folate inhibitors. We can look back at CML before BCR-ABL tyrosine kinase inhibitors. We can look at pH-positive ALL before tyrosine kinase inhibitors and say, oh, these were the patients that we've got nothing to help them with. And now they're the patients that we can serve with the most effective long-term and durable therapies. So that principle is what we need. And I think right now it's just been a really challenging time in medical sciences. It's been a really challenging time because the good work that we do doesn't happen overnight. And it's easy for me to give you these examples of huge successes, but they didn't happen from, 1 or 2 years of research. It happened from decades of research. My life was saved through an allogeneic stem cell transplant, giving another human a new immune system, which is like totally science fiction. But before that ever was a thought of a treatment modality for a patient, we had to understand fundamental immunology, like how does the immune system recognize self or not self? What is HLA and the major histocompatibility antigens? And how do the immune system avoid autoimmune immune attack of normal healthy tissue? Because without that knowledge, without knowing what the human leukocyte antigen molecules were, bone marrow transplant never would have happened. And that fundamental research that is science for science sake, that all came from international collaboration and was funded in large part by the United States government support through the National Institutes of Health. And so when the NIH is under attack, it doesn't just mean that treatments today are going to be slower because there's other opportunities. There's wonderful foundations like what was previously known as the Leukemia Lymphoma Society, now Blood Cancer United, who have really pushed to get therapies to patients. But the fundamental science that preceded that, there's no other foundation that can bridge that gap. So, for anybody who's listening here who hasn't contacted their, local elected official to urge them and to ensure that the important basic science that is leading the discovery of future therapies for cancer and for other diseases, it needs to be supported. It needs to be protected, and otherwise, there's just no way that we're going to be able to continue to make the amazing progress that we have over the last quarter century.
You argue that we need to reframe the problem in cancer instead of devising ways to kill cancer cells. We should think about ways to rewire, reprogram them. Can you explain what you mean?
Sure. So there's a couple of really um, wonderful examples where the biology has actually taught us something. And so, for people who are skeptical that doctors are just trying to make chemicals and not thinking about natural cures, there's actually a serendipitous story. So there's a rare type of leukemia called acute promyelocytic leukemia. It tends to happen in younger patients, people in their 30s, 40s, and 50s. And it's from a different translocation. Two chromosomes break apart, go back together. You see, there's kind of a theme for some of these. And here, a gene that's important for maturing your myeloid cells, which are like your first responder immune cells to the site of an infection. Um, they can't mature all the way. They can mature to like the first stage and then they get stuck. And the reason is the molecule that helps them to go through that maturation process um, is translocated to the vitamin A receptor. And so instead of being in the nucleus doing what it's supposed to do in these they're called PML bodies, the PML bodies disappear and that molecule goes outside of the nucleus attached to the vitamin A receptor. And there was a serendipitous observation of these rare patients who were cured with very high doses of vitamin A. This is the biology that explains it. So we give these patients very high doses of something called ATRA, all-trans-retinoic acid. And that molecule, in combination with some chemotherapy, because again, we do have to kill some of these cells, especially at the beginning. Could think about cancer as a garden, and the garden is trying to make the fruit of the cells that are normal, healthy blood cells, and the leukemia cells are the weeds. And if you just clip the dandelion off, the weeds that are still stuck in the soil are just going to regrow. So you really have to get it at its core. And so getting rid of the dandelions is what chemotherapy is best at. But the molecular depth of response is how well are you able to get out those roots? And so in this specific case, the combination of chemotherapy with all trans retinoic acid, high doses of vitamin A, gets at those roots. And what happens is those cells are now getting that signal that they weren't getting before. So there was the cells that died from chemotherapy, put those aside, but the cells that got the high doses of vitamin A now have the molecule back where it's supposed to go. And so that training process and that maturation process now gets to go on again. And what happens with some of these patients is actually because you had this block for so long, all these cells started to build up. You finally give them the molecule. And now, instead of having a slow and normal pace of differentiation, it's really fast. And that fast differentiation leads to a flood of immune cells that now go out in your body and oftentimes can cause problems, particularly in the lung. Now, the lung is a portal of entry, right? So if you think about what are the common, things that people get, with infections, it's how does a pathogen get into your body? Well, the aerodigestive tract is the primary mode. And so your immune cells have to be ready and primed in your lung. And now all of a sudden, if you throw a ton of immune cells into your lung where there weren't before, you could imagine that there would be such a strong response, and that strong response causing inflammation and fluid to accumulate in the lung could be very dangerous. That's something called differentiation syndrome. So differentiation syndrome, while a quote unquote side effect or a toxicity of these therapies, it's an on target toxicity, right? It's the goal. It's what we wanted to do. And I'm going to come back to this later. And the idea that if you're able to reconnect the wires and the heuristics that go on through the process of blood cell maturation can be restored. Well, now you take a cancer cell and instead of just killing it, you give it the programming that it lost, and now it can actually start to function again. And that comes with much less toxicity, much less morbidity than therapies that are damaging the cancer cells, but certainly damaging the other cells too. Now, in speaking to my own care, I receive tons of different types of chemotherapy. I got chemotherapy in my spinal fluid. I got chemotherapy in my blood. I got chemotherapy to, kind of injected directly close to my heart. And I got radiation therapy. That doesn't just affect the cancer cells, it affects all the cells in the body. And so, I follow very closely with a survivorship doctor who monitors my heart, my lungs, my metabolism, my liver, my skin, my eyes, because poison is a great tool to chop down the tree and get rid of a lot of the dandelions. But if you're using a pesticide, it's going to affect the healthy, normal plants too. And so, it's no different. There's collateral damage that happens when you use chemotherapy. Now, we worked really hard to minimize that and to dose reduce to only the necessary amount of chemotherapy to get the effect we want and to protect the healthy tissues. But it's a really challenging and daunting task. So having new tools that will change the way we treat patients is where I hope and where I expect to see cancer move in my career. We're already starting to see some other examples. There are some epigenetic mutations. So the epigenome refers to not just the 6 feet of DNA and the different nucleotides, the A, C's, T's, and G's in a row, but it refers to how that DNA inside a nucleus is organized and decorated to ensure that the machinery that's going to turn on a gene turns on the right genes in the right cell and doesn't turn on genes that don't need to be turned on. As an example, if you're going to be a cardiac myocyte, a heart muscle cell, you better express actin and myosin, the muscle core fibers. You better express something called ryanodine calcium channels, which are part of how they sense when to contract. And if you don't express those things, then you're not a cardiac myocyte. By contrast, if you're going to be a red blood cell, you better express hemoglobin. You better express the iron transferrin, the iron receptor, to be able to bring in iron and build your hemoglobin molecules. And if you can't have hemoglobin and iron transport, you ain't going to ever be a red blood cell. So the genes that define who you are as a cell and read only the specific genes in the genome, the 22,000 coding genes, and read and express only the ones that are important, are controlled by these processes that differentially shape, organize, and mark with mitotic bookmarks the entire 6 feet of DNA in that 10 micron nucleus. And so if a gene is open and it's available and it's accessible, to turn on that gene comes along, they're able to bind, it turns on the gene, it works great. But if you can't have that control of turning on and turning off the right genes at the right time and the wrong genes at the right time, well, that's kind of the start of when things go wrong. And so understanding how these molecular controllers of DNA accessibility and chromatin structure, how the beads on a string get organized, how cytosines, one of the nucleotides, is or isn't methylated. All of these processes are kind of the central command regulatory control. And many of the genes that are mutated in cancers, particularly blood cancers, are exactly these kinds of genes. And so with one of these mutations called IDH1, there's another IDH2, and we have molecules for it as well, but they haven't been quite as successful. But for IDH1, if you have a mutation in IDH1, it affects your ability to demethylate, to take methyl groups off of DNA. And we have inhibitors against the mutant IDH1, and it works great. And so a patient who has an IDH1 mutation, especially if they're not fit and young for chemotherapy, the frontline therapy is an oral pill that affects DNA methylation through blocking this mutant IDH1, as well as a drug called azacitidine. And the two of those drugs together are far more toxic than the typical myeloablative chemotherapies that we give. And so we can now use that as another example. And what we found is when we first started using these cases, these IDH inhibitors, we actually found that differentiation syndrome was happening. There's another kid on the block, which was recently FDA approved, inhibitors of a molecule called menin. And so these are what are part of a complex that is going to read the histone code, read the epigenome, and activate certain genes. And when there's translocations or certain types of mutations, this process can be unable to shut off. And so by blocking menin, we're able to evict this chemical protein machinery that's maintaining the stem cell features of these cells and keeping certain genes on. And the first toxicity we observed was that there was differentiation syndrome. They actually halted the trial for one of the molecules for quite some time, worrying that this was a major concern, a major toxicity. And I believe there was a patient that died from the differentiation syndrome process. And with that one patient's tragedy notwithstanding, this represents on-target activity. It tells us that what we're doing is actually hitting exactly where the lesion is on those cancer cells. And a colleague of mine, Shankai and Ross Levine, recently found that in patients who are receiving this, mutations happen. And in looking at the patients who stopped responding to the menin inhibitor, they sequenced them and they found where the mutation was. It wasn't in a new gene that kind of gets around the inhibitor, which is often the case. It wasn't that the gene gets downregulated, which is often the case. It was a mutation right smack in the protein where the drug binds. So the only way that this leukemia was able to escape was to acquire a mutation that prevented the docking of that drug onto its molecular target, which tells us that kind of on-target mutagenesis means that our fingers are on the pulse of this cancer. And understanding these cancers at this level of resolution is, I think, the only way that we're going to be able to make major advances. Now, many of the people listening to this podcast, particularly thinking about hematologic malignancies, may have read or heard about the tragic story of Tatiana Schlossberg. And I would say that although we've made some major advances, we clearly have a lot of progress yet to be made. The single most challenging leukemia that we know of is a leukemia called inversion 3. Here, one of the chromosomes has actually taken a small piece and it stays in the right chromosome position, but it flips. And you can think of chromosomes as having genomic neighborhoods. And those neighborhoods regulate the genes within that neighborhood in its own way. So essentially, each neighborhood has its own mayor and kind of orchestrates which genes get turned on and which genes get turned off. Those are called enhancers. But what happens in this specific leukemia is the enhancer for one neighborhood moves over to a different neighborhood. And so the cell is getting input and it says, we need more cells, we need more white blood cells. But instead of turning on the white blood cell making gene called GATA2, it's turning on a different gene called MECOM, also has been known as EVI1. And it essentially is like an immortalization gene. So now this leukemia is driven by a gene that gives the leukemia almost complete immortality. And I remember being in several large conference rooms where somebody might ask, has anybody here in this room, uh, successfully treated a patient with inversion 3 leukemia? And you look around the room at these storied master clinicians who've been taking care of leukemia patients their whole career. And the number of hands that go up, you can count on one hand. It's just tragic. So there's so much more work we need to do. Because in order for us to have these successes that we've had with menin inhibitors and IDH inhibitors and all trans retinoic acid and high doses of vitamin A, that means we really have to understand the molecular underpinnings of each different type of cancer. And to do that, it takes understanding it from a genetic level, it takes understanding it from an epigenetic level, and it takes understanding it from an immune synapse level. Because these leukemia cells aren't just happening in isolation, they're happening in the bone marrow surrounded by cells that are regulatory and immune clearance cells. And so, back in the 80s and 90s during the HIV pandemic, there were a number of cancers that were very rare that started to pop up, something called Castleman syndrome and Kaposi sarcoma. And it taught us that the immune system is always surveilling our body for cancer. And a healthy immune system should be able to identify cancer and kill it before it starts. It's led the way to checkpoint inhibitors and immunotherapy in ways that have markedly improved our tools and our armamentarium for many different types of cancers. I think the limitations on who they can cure of their cancers is still something that we need to improve. But it's this idea that the cancer doesn't happen in a dish in isolation. It happens in a human with lots of other things going on. And so we've been recently moving to understand additional layers, not just the genetic and the epigenetic layers, but also how do these cells intersect and interact with one another. And one way we've been doing that is by looking at cell surface proteomics to understand all the different proteins on a cell surface. I referenced earlier the um, self versus non-self molecules that are kind of necessary to have a successful bone marrow transplant. And those molecules don't travel by themselves. They travel in a tandem with another molecule called beta 2 microglobulin. And so, the cells on a cell surface, we can tell for, a 2 decades using something called flow cytometry. You put a cell through a capillary, there's a protein with a fluorescent marker, and if it's stuck to the right protein as it goes through, the cell will click as being positive for that fluorescent molecule, which means it expressed that on the cell surface. And that's really good information. It's given us so much ability to classify different types of leukemias. But one thing that we're starting to learn using a technology called proximity network analysis from PixelGen Technologies is that the cell surface of each cell, um, it's not binary, yes or no, I express the protein. And it's not just quantitative of I express a little protein and I express a lot of protein, but what are those proteins doing on the cell surface? Are they uniformly expressed around the cell? Are they polarized to just one end as that cell intersects and interacts with the microenvironment and the niche of the bone marrow? Are there effector cells that are engaging different cells, healthy and malignant cells in the bone marrow? And what are the combinatorial logics of how protein-protein interactions define cells and define function of cells, which has been such a cool new kind of frontier. Um, and we recently presented some of our work at their user group meeting, and we took a bunch of patients who have been treated with a doublet of kind of anti-methylation therapy, a drug called decitabine, which replaces all the methylcytosines with a cytosine like molecule that can't be methylated, and 6-diaguanine, which incorporates where your guanines are and also further prevents methylation accumulation at the methylation. And they both inhibit an enzyme called DNA methyltransferase 1. And that's the molecule responsible for copying every single methyl group, epigenetic mark, from a cell when it divides from the parent cell to the daughter cell. And so we're progressively taking away some of these epigenetic marks, something we've done for the last 40 years. But in doing them together, we had a unique and very homogeneously treated patient population. We looked to see, could we predict who are the responders and who are the non-responders before we even treated them based on their cell surface protein expression? And then once we've treated them, what do we see in terms of escape? Because understanding how cells evade hypomethylating agent therapy and what are the mechanisms of resistance would be massively helpful, both in terms of finding new therapies for them, but also in finding which patients are unlikely to respond to a given therapy. Save them the time and the misery of going through months and months of treatment only to find out it didn't work for them. And so what we found are two things. One is there are specific markers on the outside of the cell that can predict whether or not these patients are likely or less likely to respond to this therapy, which is great. We get a biomarker. But I think one thing we found that is even cooler is that one of the most stressful times for me as a care provider is I've given this patient their therapy and I knocked their counts down. And now the garden of the bone marrow is more or less empty. And I'm waiting for everything to start to regrow. And I look in the bone marrow and I send it to my pathology colleague. And we look at it under the microscope and we see some immature cells. Well, are those healthy immature cells that are going to regrow the garden? Or are those cancer immature cells that are weeds that are just going to regrow? And we can't tell. We don't have any ability to tell regenerating myeloablated bone marrow from refractory disease post-therapy. With this technology, we've actually been able to see that the cells that express this stem cell gene CD34, there's actually two populations. And based on those two populations, we can predict with near complete precision of whether those CD34 cells that are starting to regrow are good guys or bad guys. So it's not that we couldn't tell with our methods. It's just that we weren't looking at uh, the right heuristic. It's not just presence or absence. It's how do these proteins co-localize? And so the geography of each cell's protein structure is massively insightful into whether this is healthy, normal, physiological regrowth, or whether this is somebody who's still got some bad disease and we need to just keep going after them because I'm going to treat them totally different. Somebody who has recovering marrow gets time off, gets a break, let's let them recover, and then let's check their bone marrow and see if their counts have recovered, whereas somebody who has residual disease needs more therapy because otherwise all that's going to come back are a bunch of leukemia cells. So it's been a really cool finding there, and we're starting to get that put together for upcoming manuscript, largely computationally driven and experimentally driven by Dr. Yi Chen, wonderful postdoctoral scientist in my laboratory, and so we're really excited to share that.
As I understand it, the pixel gen technology allows you to get a sense of the view of the networks as opposed to a single marker on a cell. What are you able to do with this data, and how might it lead to new ways to both address hematological cancers by targeting epigenetic drivers, and how might you use this as a tool to optimize treatment choices for patients?
Perfect question. So I'll answer the second question first because that's the one I feel like we've already been able to hopefully make some headway. Is use this as a biomarker. So it's not just presence or absence or abundance or non-abundance of a certain protein. It's how does that protein localize with other proteins on the cell surface, and does that proximity fingerprint, that proximity geography, represent a biomarker we can use to say healthy cell, not healthy cell, and what should be the next clinical move. But the first question is actually one that, while I'm not particularly well suited to answer, I have some really exciting colleagues here at Columbia who I've started to work with. So Dr. Sasha Hobner and Dr. Adam Glasgow are two colleagues of mine. And what we hope we can do is actually take this information and use it to make better cell therapies. And so, for 20 years, we've said we find cells that express a certain protein and we want to get rid of them. And for example, in many B cell cancers, we can use an antibody called rituximab, and that antibody is going to go stick to the CD20 on the outside of those cells, and it's going to tell the immune system to attack, and it's going to drop them. That works great. Expanding on this, for refractory patients, many folks, Michelle Satterline, Carl June, Rainier Brentjens, and others developed T cells that were aimed at targeting that same molecule, CD20. And that CAR T cell therapy is a therapy that didn't exist when I was treated. But if bone marrow transplant didn't work, I didn't have any other options. And now there's other options. Now, CAR T cell therapy has been an enormous success. And it has been an enormous success in B cell cancers and a little bit in myeloma with some of the antigens they target for myeloma. But I think one really unmistakable fact needs to be recognized. We got really lucky with CD20 because it fits three key essential aspects of what's needed for CAR T cell therapy to work. One is the protein has to be abundant on the cell. There has to be a lot of it so that it's able to recognize it effectively. Two is the leukemia can't live without it. So if CD20 didn't exist, then that leukemia ain't happening. That CD20 molecule and its signaling is so essential for the leukemia that there's no way that it can survive without it. And then third, the patient needs to be able to survive without it. So if you have no CD20, is the patient going to be okay or not? And if you look at most of the failed CAR T cell therapies to date, it's usually one of those three things that is the reason for failure. Either there isn't enough of that protein for the CAR T cell to recognize all the cancer cells. What's most common is you target something on the cancer cell, and the cancer cell says, "Oh, you don't want me to have CD33? No problem. I'll just turn it off, and I'll epigenetically suppress expression of that protein. So now I will be immune from that CAR T cell." And the last is if you give a CAR T cell against such an important molecule like CD123 or CD90 that's important for normal stem cells, that the toxicity is just too great because while you're killing the cancer cells, you're also killing the essential cells that are going to keep that patient alive by making blood through, continuing after their therapy. And so single molecule targeting strategies for CAR T cells has given us some successes, but not as many as I think we would have liked. What I'm excited to hope to use this technology for, and granted these are data that are super in their infancy, is can you develop logic gating such that it's not just a single protein, but I talked about how that proximity geography can be a fingerprint to the bad cells versus the good cells. Well, are there tandem proteins that when in close proximity are the specific marker for the cancer cell? And now you're not just targeting anything that expresses protein A or anything that expresses protein B, but if you're expressing protein A and protein B close together, then can you develop a bi-antigenic targeting T cell to attack and clear that specific clone? So those are things. This is all like just starting to get started with, but I think we have exactly the right personnel and the right technology and the right talent here to really make some important headway going forward, both from target identification, from a biomarker standpoint, and ensuring that we have precision therapies of getting the right patient the right therapy, but also, keeping from treating patients with therapy that we otherwise would think would probably be futile, and redirecting that patient to more appropriate therapy. So certainly there's so much work to be done, but my life was saved thanks to the work and the science that came before me. And folks like E. Donald Thomas, who developed allogeneic stem cell transplant, folks like uh, Sidney Farber, who developed many of the molecules attacking folate inhibition, and my many admired colleagues who've trained me to take care of leukemia patients. Um, they all did so much to make it possible for me to not just survive a cancer, but to survive a cancer and really have a life that resembles somewhat similar to what it would have been prior to cancer. I'm the proud and lucky father of two beautiful daughters. I have a wonderful, beautiful wife, and I get to work in New York City at an amazing institution where I have a laboratory who works with me to try to keep moving the puck forward and keep advancing the science such that we can help these patients who desperately need our help.
Now, what's the potential to ultimately change the research and treatment paradigm for these cancers and the outcomes for patients?
Yeah. No, it gets this idea that, I think most people have kind of started to appreciate that cancer is just not it's not that all cancer is cancer. And it's not even that all lung cancer is lung cancer. It's cancer is a disorder of the genome. It is a genetic disorder that happens in a context that can be the genes you were born with it, the genes that you were born with, the random mistakes that happen over time, the chemicals and environmental factors that we're exposed to. But there are events, random and non-random, that affect our cells' DNA and response. And understanding what was the inciting event and the mechanism of how that cancer arose is exactly what needs to be known in order to find the right way to treat them. And we have such wonderful examples when that works, but they're too few and far between. And the hope and the dream is to have precision oncology options for every single patient who walks through the door here at Columbia University Irving Medical Center.
Aaron Viny, hematologist and medical oncologist and assistant professor of medicine at Columbia University Vagelos College of Physicians and Surgeons. Aaron, thanks so much for your time today.
It was a pleasure. Thank you, Daniel.
Thanks for listening. The Bio Report is a production of the Levine Media Group. To automatically download this podcast each week, subscribe to our RSS feed or through iTunes or other podcast manager. To join our mailing list, go to levinemediagroup.com. We'd love to hear from you. If you want to drop us a line or are interested in sponsoring this podcast, send an email to danny@levinemediagroup.com. Special thanks to Jonah Levine, who composed our theme music, and the Jonah Levine Collective, which performs it.